So this is chapter 5 on radiation and spectra. We are taking a little break from sun, earth, moon, sky, astronomical events, and we'll look little more detail into the physics of light or radiation, atomic spectra, the electromagnetic spectrum, what that is. And so this is more of physics of light. And light is a wave that you'll see in a minute. And so we'll look into the physics of these waves. Light travels as a wave, similar to water waves, sound waves. And so we will, look at the microscopic view of the light waves. These objects, the stars, the galaxies, asteroids, of the planets, the 5,000 planets that NASA has discovered, or I should say, there are other organizations too, universities, individual professors. All these are not miles away. They are hundreds of thousands of light years away. So there's no way to get to those planets, those stars, to physically study their property. So the only way is to study about those stars by studying the light that has reached us here on Earth. And remarkably, we can, decode the light that has reached us from a galaxy, star, nebula, all the supernova explosions. We can study the property of the light and understand the property of the star or the galaxy cluster, or supernova explosion. And so study of light, understanding light is very important. The nearest star, Alpha Centauri, Proxima Centauri binary star system, 4 light years away, but it will take us more than 100,000 years to get there with the best technology we have. Not 1 year, not 100 years, 100,000 years. Can you imagine how long is that time frame? The Homo sapiens that evolved in the African coastlines, that's 100,000 to 200,000 years old. The human civilization has, is, I shouldn't say civilization, the human kind, the biology has evolved for about 100,000 years. So from Homo sapiens, almost monkey-like, to us, it's been 100,000 years. And now getting to the star, nearest star, and there are billions out there, it's going to take 100,000 years. So it's practically impossible right now to study those objects by any other means. So the only way is to study the starlight. This is the sun in a different wavelengths. Light that we see is all visible in the optical range or in the visible range. In that rainbow spectrum, blue to red, those are visible spectrum of electromagnetic wave. The electromagnetic spectrum extends from very high energy waves like the X-rays and gamma rays to visible to radio waves, very less energetic waves. So in between, somewhere there lies the visible. Our eyes can only detect that visible part of the spectrum. We cannot see alpha ray, gamma ray. We don't see Bluetooth, Blu-rays, the Wi-Fi. If we could see, then this room will be full of, your phones would be emitting these Blu-ray, Bluetooth rays, infrared. These lights will be emitting all these UV, infrared radiation. To understand the largest object in the universe, we need to look at the smallest matter in the universe. And those are the constituents of atoms, like what atoms are made up of. Um, Usually, we take these small element atoms. That's the periodic table of the elements. On the wall, you can see here in the diagram we are showing helium atom with 2 protons, which are positively charged, 2 neutrons, which do not have charge, but they help to glue these positively charged particles together inside the nucleus of the helium. And there are electrons, around its orbit-like structure. And these are the innermost orbit, which can hold up to 2 electrons. Anymore, like for lithium, beryllium, boron, carbon, the shell, outer shell would increase. The distance between the first shell and the nucleus is about 10 power minus 10 meters here. And again, these are 2 important fundamental particles. Electron is a fundamental particle. We cannot break electron any further. However, protons can be broken into other subatomic particles. And in high energy physics, we have a different standard model table that looks like periodic table of the elements here with all these subatomic particles. That's for some other day, though. And so there are these two important, 2 main particles, electron and protons. Protons, they have 2 important properties. One is they have charge, the other they have mass, and also they have different flavor of charge. We named it electrons to have negatively charged, protons to have positively charged. And these were the important findings of 18th, 19th century. And these electric charges by itself have electric field around them. If I set a positive charge in space, it sends out this electric field outward. That field travels at some speed, and both charges have electric field, the positive charge or the negative charge. And we also found that the moving charges, like the electrons, what we call current, the moving charge is basically current. Current is the rate of flow of charge per unit time. We found that for any current carrying wire like this one here, if it has it does have current in it, like this pointer here, it has some form of current, electrons passing through it. And we found that there is always magnetic field surrounding this wire. Okay, so by electron itself or a proton itself, charge at stationary charge have electric field around it. Okay, again, I'm talking 2 different fields. So when these charges move, now they have magnetic field as well. So basically, current carrying wire or current or moving charges produce magnetic field. And there's this magnetic field. These magnetic fields are oscillating because the electron tend to vibrate. They create this wave-like structure, wave of electric field and wave of magnetic field that looks like this. And so the biggest discovery of Maxwell was that these, whenever, so it is color coded, blue is electric field, red is magnetic field. Magnetic field is denoted by B, capital letter B, electric field is capital letter E. Whenever these oscillating electric field travel through space, they also generate oscillating magnetic field. And there is another law that says the oscillating magnetic field generates oscillating electric field. So it's like one producing the other. One triggers the other. So that was the biggest breakthrough, because if we were able to set, that's what the antenna does. Using antenna, if we are able to set initially the oscillating electric field, then that will create oscillating magnetic field, and they travel outward in time. And so even now that production is stopped or cut off, then this is now a self-fueling wave that travels outward. And that's what all these waves are: the radio waves, the FM waves, the Bluetooth wave, the wireless. These waves are basically oscillating electric field and magnetic field intertwined to each other. They're always perpendicular to each other when they crisscross like that, shown here. And Maxwell also calculated, he was able to calculate the speed of this wave. And he found that that speed is same as the speed of the electromagnetic wave. Any wave that has electric field and magnetic field intertwined. He found that the light has the same speed as the electromagnetic wave. As a matter of fact, light, the visible light that we see of all colors that are visible to our eyes, they are all part of electromagnetic spectrum or electromagnetic radiation. And just like the water waves, waves are produced primarily by the vibration of any object. The sound that's coming out of my mouth is a sound wave that is produced by the vibration of the larynx. When my larynx vibrate, every word, every letter, every piece of sound has different energy, different wavelength, different frequencies. So sometimes my voice is high pitch, low pitch, and like that. So the vibration by the frog's leg here is creating the water waves, and that wave carries energy with it and travel outward, creating the ripples in the water. And when that water hits some grass leaves out here, those leaves can vibrate as well. Same way, whenever the FM or TV station plays something, they convert that TV signal into the electromagnetic wave. So those waves travel in space, and whenever they hit the antenna, the receiver in our TV, or your antenna in your car, if you are listening to any FM, so that FM, it's whenever songs are played, when the DJs, the RJs, when they talk, their sound wave is a mechanical wave. It's not electromagnetic wave. Sound waves, water waves are mechanical waves. They need medium to travel. Those are converted by some electronic equipment into electromagnetic signal, and now that electromagnetic signal travels at the speed of light, and when that wave hits the antenna, the electrons in the antenna are triggered and they vibrate at the same frequency as the FM station is sending that signal, and that antenna receives that signal, converts it back into sound wave. That's what the interior of a radio does, or TV signal, and you hear the sound again. That's the whole mechanism. Let's look into a little more detail what the wave looks like, or the characteristic of a wave. Like I said, sound waves, water waves needs medium to travel. Medium, right now you can hear me, my sound is traveling through the air molecules. If there is no air molecules, there is no atoms in between you and me, you will not be able to hear my voice. Like if we are in space, it's vacuum there, we will not listen any sound because there is no medium. However, the electromagnetic wave that does not need medium, and we know that because all the light rays coming out of the sun or stars are electromagnetic waves, and there is a big vacuum in between us, yet those light travel to us, right? We see them, we receive them here on Earth. So electromagnetic waves do not need a medium. Maxwell calculated the speed of electromagnetic wave, which is also the speed of light, because light is an electromagnetic wave, and that's in vacuum. This speed reduces very slightly when it enters the air medium. And that speed is 3 times 10 power 8 meters per second, or 300 million meters per second. And that's also the fastest possible speed in the universe. Nothing can travel faster than this speed. This is the speed limit in the universe. And any wave motion can be characterized, any wave, and this applies to either it's a water wave, sound wave. We can characterize like this, a simple wave, or electromagnetic wave. We can give certain names to it. We call that the high part, the mountain, the crest, the valley is the trough, and the distance between crest to crest, or one complete cycle. It can be distance to trough, or I can also measure from this point to that point, because this is one complete cycle. This length is called wavelength. That's the crest. And there are two types of wave, transverse wave and longitudinal wave. It has to do with how they travel. Like all the electromagnetic waves, sound waves, not sound waves, the water wave are transverse wave, meaning the particle movements is perpendicular to the direction or direction of motion. So this transverse wave here, it's oscillating like this, but the wave travels, to the right. However, for the sound wave is the compression and rarefaction of the medium, and which is like this. So sound wave does not travel like this. It compresses the air medium, and it relaxes, and it compresses and relaxes. So that's pressure amplitude, makes the sound wave go forward. So hence that's called the longitudinal wave, sound waves. Here is an example of a sound wave, and this is the transverse wave. Again, that distance, the trough to trough, crest to crest, or pick any point and complete a cycle. That's called the wavelength. Okay, it's not just that, there are more terms associated with a wave. These are important terms. Please memorize or know these definitions, because from now on I'll simply use frequency, and you should know what frequency is, what wavelength is, what time period is, and so on. So like I said, wavelength is a distance between the crest or troughs, or as a matter of fact, you can start at any point, complete one cycle, that's your wavelength. Time period, and by the way, symbol here, it's lambda. For wavelengths, we'll write lambda in the equation. When you see lambda, that's the wavelength. Its unit is meter. Time period, it's either T or capital P. That's the time period. Time period is time taken for the wave to make one complete oscillation. If the wave starts here and it goes down and comes back to the same point, so it basically completed one cycle. Then from here it starts to go down again. And so this is the one-time period. Frequency is number of cycles in 1 second. 1 second. Sometimes these cycles can be more. Sometimes the wave makes 1 million cycles in 1 second. That's its frequency. So cycles per second. Sometimes it may make just one cycle in 1 second. So its frequency is 1 hertz. The unit of frequency symbol is F, small letter F, unit hertz, HERTZ or HG, not the car rental hertz. Then speed. Speed is the general term, the rate of change of position, how fast position changes with respect to time, gives us speed or velocity. Units meters per second. And so finally, for any wave motion, the speed at which a wave moves equals the frequency times the wavelength. This is an important equation that, and C here is reserved for the speed of light. Usually speed is, the symbol is V. Speed of anything, your speed, your running speed, walking speed, car speed, driving speed, airplane speed, these are usually V for velocity. Again, velocity is a vector quantity. It has magnitude and direction. Speed, when you say speed, it's just a magnitude. But this C, we reserve it for the speed of light. So that small letter C is a symbol for the speed of light, 300 million meters per second. We will always keep that, reserve that letter, C for speed of light. And there's this important equation that speed of light or speed of any electromagnetic wave can be written as the wavelength of that wave versus times the frequency. Next you will see the whole band of electromagnetic spectrum that constitutes of radio waves, gamma waves, UV, visible, ultra UV, and radio. All that means they all can have different, they all have different wavelengths and different frequency. But as long as you know lambda and F, you can calculate their speed, or the vice versa. For example, what is the wavelength of visible light? A visible light that has a frequency of 5.66 times 10 power 14 hertz. We have frequency. We need to find the wavelength, lambda, and we know C. C is constant, even though the question doesn't give you here. I just posted it earlier. And so I can solve this for lambda, which is C divided by F. Everything is in the unit, right unit. Frequency is measured in hertz. The speed of light is 3 times 10 power 8 meters per second. Lambda divided by this is the given frequency. That's about 5.3 times 10 power minus 7 meters, or 530 nanometers. 530 nanometers. 1 nanometer is 10 power minus 9 is nano. So that's 5.3 10 power minus 7 is equivalent to 530 times 10 power minus 9. 10 power minus 9 is nano, hence that's 530 nanometer, which is in the yellow-green part of visible spectrum. We'll come to that visible spectrum in next few slides. Similarly, we can calculate the wavelength of FM signal of 93.3 megahertz. Mega means million, 10 power 6. Mega is 10 power 6. So 93.3 is 93.3 times 10 power 6 hertz. You have to convert megahertz to hertz when you do the calculation here, which is 93.3 times 10 power 6. And hertz means that's the units of frequency is cycles per second. So frequency F, the unit. So this is wavelength. No, this is the frequency in megahertz. So F, for this F, if I can write, if it is 10 hertz, that means 10 cycles in 1 second. In 1 second. This 1 over second term, 1 over second, this is written as hertz. Or the unit of frequency in standard unit, you can call it per second. Okay, that's what it means here, 93.3 per second, which is same as saying hertz, H-E-R-T-Z, hertz. And so the wavelength of a FM radio wave is much bigger, 3.22 meters. What's the difference between a radio wave and an FM wave? As you may have realized, radio waves travel much farther out. Like you can hear NPR that's being played from Washington, D.C. here in Texas. Radio waves. They have lesser energy than the FM wave signal. FM wave signal is around 90 megahertz to 100, 105 megahertz. They have higher energy, and that translates into a better quality sound. So it's listening to MP3 versus HD, Blu-ray, 4K version. And but the catch is these FM signals do not travel that far out. They have high quality, but they are limited. So high energy wave travel shorter distance compared to low energy waves. Low energy waves travel farther out. So the radio signal does not sound as HD version as the FM signal. And so now next, again, this is all about light. Light as a photon. Photon is a particle, smallest particle that make up the light. Wait a minute, I just said light is a wave. Wave means a continuous band of any structure. It's continuous. There is no discrete. There is no disconnection. Wave is a continuous thing. But surprisingly, light also behaves like it has a discrete particles in it. So it has a duality, dual nature. We call it particle-like and wave-like, or the vertical-like, or the vertical. And it has been tested again and again. There have been thousands, millions of experiments done using light, and light behaves both the wave-like and the particle-like. So the experiment have been as proven. And so particle-like, so the particles of the wave, the sound, the light are called photons. These photons are energy packets. They are massless in a way. These are massless energy packets that travel through space and time. and at the same time they behave like wave. And the light, by the way, here the interference, the wave interfere, like the water waves interfere, sound waves can interfere, and there's interfering waves. When they interfere constructively, the amplitude rises, and destructively, it destroys the amplitude. So two light waves, when they meet, and it happens only for waves, when the waves meet constructively, it creates a constructive interference or brighter band of light. And there have been many experiments like the property of the light called the interference and diffraction. Those experiments have proven that the light creates this dark band and white band, proving that the light is a wave. And none other than Einstein himself, using photoelectric effect, so that energy is proportional to frequency, which is called the photoelectric effect. He showed that light is a quanta of particle, quanta of energy. When that hits any metal surface, the electron in that metal surface gets out with the same energy as the incoming photon. So that proved that light is also a particle. And that realm all takes us to something called the quantum mechanics. And not just photons, the electron that we discussed earlier, electron also behaves like a particle and a wave at the same time. And that's begging us to ask the biggest question in physics, that is the universe wave-like or the particle-like? Is the universe discrete or continuous? Big question. We don't have any definite answer to that, because the fundamental thing that we know, like electron and photon, they behave both. Okay. And the next thing is the inverse square law. Light coming out from any source, like a star here, and we are measuring in a certain area A. So all the light that enters this area A, and it travels some other distance, marked 2 meters here, it's the same amount of light that reaches this region here. But you see, since they move outward in all 360 degrees, that's always expanding, increasing in the area. So now the intensity that was here is divided into 4 different regions. It's the same amount of light, but it has to cover a larger area, so the intensity goes down. By how much? It's always by 1 over distance squared, or 1 over r squared, hence it's called inverse square law of light. For example, the intensity of a 120 watt light bulb, any light bulb in the ceiling, observed from 2 meters away. If you're measuring at 2 meters, the intensity is measured in watts, and so that's power per unit area. So watts per meter squared. This would be squared, meter squared. It's 2 meters away is 2.4 meters squared. Now, if you double the distance to 4 meters, so that's 2 to 4. So that's double, means you go from 2 to 4, but it's an inverse square, so you square the distance 2 power 2, which is 4. So you are actually reducing the intensity by 1 over 4. So it goes down 1/4 by doubling the distance. If you triple the distance, 1 to 3. So you go from 2 meters to 3 meters, but the intensity goes down by 1/3 squared. So that's intensity is reduced by 9 times. That's what the inverse square law is. So that is all the behavior of the light. Next section is the electromagnetic spectrum. Another important section to understand the not just light, the whole band of the spectrum. We will try to understand. How each of the spectrum differ from one another. How these different band of lights, visible, invisible lights, interact with our Earth's temperature, Earth's atmosphere, and how they depend on the temperature. So, these three things that we'll try to answer in this section. This is actually a concluding slide. I want to start with a concluding slide. This is the whole spectrum of electromagnetic band, or that's why it's called the electromagnetic spectrum. It has all the energy or electromagnetic waves that we know of. Start from left here, top, you'll see the wavelength. You know what wavelength is. Frequency at the bottom. So the names here, the radio waves. Radio waves have the largest wavelength. Here, 30,000 meters. So the wave, the distance between trough to trough is 30,000 meters. These are radio waves, and you see as you go to the right, the wavelength decreases between going from radio waves to microwaves. Here are all our radars. Somewhere in between you'll see AM radio waves. Your TV waves, channel 2 to 6, have longer wavelengths than channel 7 and up. Your cell phone wavelengths are around here, and it starts infrared, ultraviolet, X-rays, and the gamma rays. The shortest wavelength waves, very short, 3 times 10 power minus 12. That's picometers. And as you see, as the wavelength decreases, the frequency starts from 100 Hertz and the frequency increases, and you have frequency as high as 10 power 20 Hertz for gamma rays. Okay, and in somewhere in there between 750 nanometer wavelength, nanometer, or in terms of meters, 7.5 times 10 power 50 meter, in this range here lies the visible light. Why we call it visible light? Because it's visible to our eyes. Our eyes, you see the electromagnetic band, how big it is? But our eyes only sees 700 nanometer wavelength to 750 nanometer to 400 nanometer only. Why? Well, that's how our eyes evolved from the evolution process, and it has also to do with how the Earth's atmosphere and the sun. Sun produces all this band of light from gamma rays to radio, but our atmosphere blocks almost all of these. Our atmosphere only allows, some UV, but it only allows most of it in this range, 750 nanometer to 400 nanometer. So when we evolved from cell to higher order organisms, chimpanzees, whatever, Homo sapiens, to now, since Earth only received in this frequency, in this wavelength range, our eyes didn't need to detect X-rays and gamma rays because it was not present. That's what evolution is. It adapts for the best, for best result, for best viewing. And so the range, so you see the red here, 750 nanometer versus 400 nanometer. So the energy increases as you go from left to right, because gamma rays are much high energy particles compared to radio. Within visible, the red band is less energetic waves than the blue band. That's what the color also represents. When you're cooking in your gas, the blue flame on the top, blue means more hotter and also more energetic. The waves, the blue waves, are more energetic than the red waves. But there is also a catch. You see, these low energy waves of AM travel farther out. In the same way, the red light can travel much farther because it has less energy than the blue lights. Red lights have longer wavelengths. They interact less with the atmospheric particle, hence they can travel farther. And that was the reason we chose the traffic light to have red as the emergency, to stop. And it would be visible from much farther out. And even when it was foggy, cloudy, rain, the red light would travel farther more than any other color. Hence, the red light was chosen as the emergency stop light. And so this is the whole, the electromagnetic spectrum, everything shown here as we receive from the sun. So sun or stars are outer objects. So up here, let's keep our sun up here, and sun emits all form of light, visible, invisible, so that whole electromagnetic spectrum. But there is atmosphere which kind of protects us, and blocks here. All the gamma rays, X-rays are blocked right here within stratosphere. UV have three different energies. Some are strong UV, weak UV, or longer wavelength versus shorter wavelength. Long wavelengths are weaker UV, so they penetrate little deeper, about 4 or 5%. They call it UVA, B, C. A is the weakest, C is the strongest. We don't receive B and C, we receive A about 4 or 5%. That's why there's a UV warning. We get sunburn. Prolonged time of that exposure to UV may cause skin cancer and such. So some of them reach here, Earth's surface, usually in the higher altitude, because they interact with the air molecules. The lower surface may not reach as much. Infrared, not much, but you see the radio. This is the radio window here. They reach the surface of the Earth, and you go farther, longer waves, weaker energy. They may just be blocked somewhere out here. So on Earth, we receive the radio signal, not just from sun. We receive from other stars, other galactic systems. We can receive that. And you see, most important, we receive the visible range. And most of the high energy signal or high energy waves are stopped within stratosphere. Very important. And so here are all we detailed explanation of each of the rays. Gamma rays. These are the shortest wavelength and highest energy. Short wavelength, and so I'll draw like this. So this is a wave, and as I decrease the wavelength, it looks like this, and maybe more like just like that. So this means here this is the longest wavelength. This is a very short wavelength. This is in the radio range. This is in the gamma. Gamma is the Greek letter gamma or gamma rays. So it has short wavelength but very high frequency. That high frequency makes it able to interact with the atoms in a short distance. And it's no longer than 0.01 nanometer, which is 10 power 9 meters. These gamma rays or X-rays down here, they can be created within stars. Sometimes the collision of stars produce that. Also, the nuclear reaction, some radioactive materials produce gamma rays and X-ray, and that's how we generate X-rays in lab, because we need especially X-rays. You have done X-rays in your life, or maybe not. I've done plenty of times. That's because X-rays can pass through flesh, soft tissue, and they are blocked by the bones, harder tissues, and it creates an image of a bone. So those X-rays are created in lab for medical purposes. The gamma rays, they can be harmful. Even X-rays can be harmful because, again, they are high energy waves, very short wavelength waves. They can interact with your tissue, and they kill the tissue, basically. That's what the radiation poisoning is, and gamma rays are known for that. The X-ray imaging, another important thing. The sun, as we see, we only see in the visible part, from blue to red, because that's our eyes can detect. The X-rays do not reach the ground, so there's no way we'll see the X-ray image of the sun from ground, but we can fly up in space. We have telescopes up in space where the X-rays from the sun are received, and as they hit the X-ray detectors in that X-ray telescope, we can image the sun as if that our eyes were detecting X-rays, which we don't, but we have a telescope that detects X-rays. So the sun would look something like this in X-ray. This is more of a combination of X-rays and UV of the sun, how it looks. This is X-ray image of the whole galaxy. This is the band of Milky Way. You have seen Milky Way in visible red to blue, pretty band of Milky Way, but this is more, you see, when you only look at the X-ray region, the energy equivalent to X-ray waves only, and not the visible. The other, again, ultraviolet, radius intermediate between X-ray and visible. In between there is a UV or ultra. So this is little ultraviolet. Violet is the last end of the spectrum in the visible range. So that's little beyond violet is ultraviolet. And it's in between X-ray and visible. Is the wavelength somewhere from 100 nanometers to 400 nanometers. Wavelength 400 nanometer to 750 is the visible. Again, which is this visible light between 400 700 nanometer, and this is something we see, or even our cameras are designed to see. This is the band in the electromagnetic spectrum that easily reaches the surface of the Earth. And as I explained earlier, we human beings were evolved to detect within this frequency or within this wavelength. There are some creatures, some birds, bat, like they can see at night, means they can detect in the infrared region and they see at night because that's how their eyes evolved. And just here is a visible light example how pretty it can be. I took this photo on my way to Mount Everest Base Camp in, I think it's 2018 or 19. Okay, there are others, radiation, infrared, microwave, radio waves.